In this video, we're going to be discussing how to graph a logarithmic function. And to begin this concept, what you want to know is that logarithms are really just inverses of exponents. So I think it'd be a nice thing to take a regular function, 2 to the x power, an exponential function, and then go ahead and find the inverse, and that's going to be a logarithm, and then graph that and see how the two compare. So right down here, f of x is equal to 2 to the x. We're going to graph this, and we could graph this with a table. Go x and f of x. So we can start with a nice domain of maybe -2, -1, 0, 1, and 2. Move this up a little bit. And 2 to the -2 power would be 1 over 4, 1 over 2 squared. And 2 to the -1 power is 1/2. 2 to the 0 power, that's 1. 2 to the first power is 2. And 2 squared would be 4. If we plot those here, we've got -2 and 1/4, -1 and 1/2, 0, 1, 1, 2, and then 2, 4. We get this nice curve that will look a little bit like this. Now keep in mind that the value of f of x, or y in this case, cannot be lower than 0. As a matter of fact, it can't even be 0. Remember, there's an asymptote right here, y is equal to 0. Remember that when we're graphing inverses, inverses are symmetric about the line y is equal to x. So I'm going to graph that right here in green. And let's see if I can make it all the way to the edge here. So that'll be the line y is equal to x. This is not an asymptote, this is just the line of symmetry. After this, to see what the graph of the inverse of 2 to the x would look like, we know that it's going to be symmetric about this line y is equal to x. We're going to take this graph and it's going to look a little bit flipped. So it's going to look something kind of like this. Let's go ahead and do a little bit of math to figure out what that inverse is. And remember, to find the inverse, what we want to do is we want to switch the x and the y. Remember, f of x is just y. So I'm going to have x is equal to 2 to the y power. If I solve here for y, we can use our log form. So we could go log base 2. We're going to be solving for the variable, which is y. And then we have x here in the argument position. Remember, this is not just regular y, this is really the inverse because we switched the two. So if you wanted to write this in function notation, you could write the inverse of, f of x is equal to log base 2 of x. So I'll write that down here and we'll investigate what's going on with this function here soon. So we've discovered that the inverse of f of x is equal to 2 to the x is log base 2 of x. Also, keep in mind that it's also x is equal to 2 to the y power. Yes, the y is not solved for, and here it is, and we can write this in our inverse function notation. But this is also an important thing to realize as well. So I'll move this up just a little bit so you can see the entire graph. And what we're going to do here is we're going to graph x on one side here, or do a table, and then on this side we're going to have the inverse, or in this case it's just y. If you can think about these logarithmic functions just as being exponentials, it can really help you see what's going on in these situations. And you can tell here that if we choose a value for x, we could go ahead and solve this, and that would work just fine. Or, in this case, if you choose a good value of y, it can be very easy to find the x value that goes along with the y as well. So on the left-hand side in blue, we chose values of x, and that gave us f of x. Here we're going to choose the values of y, and that's going to give us x, so we're going to kind of go in the reverse order, just like you would switch the x and the y to find the inverse. So for y, we're going to pick a nice range of -2, -1, 0, 1, and 2. if we substitute negative 2 into this equation right here, we've got 2 to the negative 2 power, which is 1/4. And we can look back at the example in blue, which is just y or f of x is equal to 2 to the x, and you can see that the x's and the y values are now just going to be switched. So negative 2 comma 1/4 would be 1/4 negative 2. 2 to the negative 1 power is 1/2. Same thing happens. The x and the y just switched, just like we switched it over here to find the inverse. 2 to the 0 power is 1, and then 2 to the first power would be 2. 2 squared would be 4. So it's a little bit weird to get used to at first because normally, especially in your past math classes, you probably just chose values of x. And you could definitely do that here. But I think it's a little bit easier to choose values of y because we can really just evaluate these very, very quickly. We know our exponent notation, and we can find our corresponding values of x. So to graph these, keep in mind the 1/4 is now x, and the negative 2 is y. So we still start at the origin. We're going to go right 1/4 and down 2. So that's the first point. 1/2 comma negative 1. Well, right 1/2 and down 1 would be here. Right 1 up or down none would be right there. And then 2, 1 would be right 2 up 1. And then we've got right 4 up 2. So we could go right 4 up 2. And you're seeing here that this shape, this curve, is very similar. As a matter of fact, it's the exact same shape. It's just reflected over the line y is equal to x. So if we draw this, it's going to look a little bit like this. Keep in mind that this end of the graph will get very close to the y-axis, but it won't cross over. Remember that in this case, x cannot be negative. If we look at this equation right here, the inverse of f of x is equal to log base 2 of x, remember that this position right here, the argument, cannot be negative. If you take a look here, 2 to a negative power just gets us something close to 0. And you could make this arbitrarily as negative as you wanted to. You still wouldn't get to 0. You'd get very close to 0, but not exactly 0. Or any negative value for that matter won't work here. So if we compare that to the graph in blue, the asymptote here was y is equal to 0. The asymptote here is going to be x is equal to 0. And I'll shift this up just a little bit so that we can make a few comments here in the bottom. And so if we were to analyze this function here, the one in red, one of the asymptotes, instead of the old graph, y or f of x equal to 2 to the x, that's y is equal to 0, it's now x is equal to 0. So the asymptote is x is equal to 0. So the x's and y's are just switched. If you think about your domain for the graph in blue, the graph in blue's domain is any real number for x. You can plug anything you want in for x. Fortunately, though, we said that x in this case, in the inverse, the one in red, cannot be 0 or anything less than 0. So if we wrote the possible values of x, which is the domain, we're going to need to write 0, comma, infinity. You can see that this graph in red exists for all values for x that are larger than 0 or greater than 0. So in interval notation, we want to write 0, comma, infinity, not including 0. The range, then, is going to be the possible values of y. And you can see that this graph, if we make x arbitrarily big, then the end of this graph here continues to grow and get bigger and bigger. As a matter of fact, it will continue to grow if we pick large values of x. Also, this graph exists all the way down. So this the range for this graph is negative infinity to infinity. So let's just do an instant recap. If you want to analyze this graph, what you do is you basically just switch the x's and the y's from an exponential function. So the asymptote for the blue one is y is equal to 0. Asymptote is now x is equal to 0. The domain is what the range was for this graph, and it's 0 to infinity, and the range is what the domain was for the graph in blue, which is negative infinity to infinity.